So we're doing some interesting facts about centroids. So the Theorem of Pappus. There are actually several theorems of Pappus, but the one we're talking about has to do with centroids and volume. So if we have a simple plane region, so a simple plane region just is, we've been talking about planar lamina. So a simple plane region is just some kind of planar lamina. And we're going to revolve this simple plane region around an axis. So we have some kind of shape, some kind of planar region, and we're going to revolve it around this axis. The Theorem of Pappus P-A-P-P-U-S. Theorem of Pappus says that the volume of the solid generated when we rotate this plane region around this axis is the area of the region times the distance that the centroid travels as it rotates around the axis. So if we think about some plane region, trying to find that volume of the solid using disks, washers, something to find the volume of some arbitrary plane region, depending on the region, it can be really difficult. Well, the Theorem of Pappus says all we need to know is the area of the region. We need to know the location of the centroid, and then we can figure out the volume of revolution. All we have to do is multiply that area by how far the centroid travels around the axis. So another way we could write that is the volume is 2 pi, and I'm going to put r bar times the area. And r bar is the distance from the centroid to the axis. So 2 pi r is just the circumference of the circle that centroid travels, and we multiply that by the area of the region. So if we have a nice simple region like a circle or a square or a triangle where it's easy to locate the centroid, we can find the volume of revolution by multiplying the coordinate of the distance from the centroid to the axis by 2 pi, and then by the area of the region. So I find the Theorem of Pappus a really kind of nice result, a nice extension of centroids, because if we have it, like I said, if we have a nice simple region, we can find the volume very easily. Because we can find the centroid, if we have a nice shape, we can find the centroid easily. Now, if our plane region is complicated, it can be more complicated to find the centroid than it is to find the volume of that solid of revolution by some other means. An interesting interesting exercise. It's not difficult to show that the theorem of Pappus is true. So if you take an arbitrary plane region and find the location of the centroid by the techniques that we've used and compare that to the volume of revolution using methods that you've already learned. For a region like this, you could use cylindrical shells, and you can show that they're the same. Yeah. Centroid and center of mass are the same in if the distribution the distribution of the mass is uniform. If it's not, then it can be different.
But you find them the same way.
Right, right. So centroid, and the distinction I made the other day is centroid. We usually, when we're saying centroid, we're assuming that the density is uniform. So the centroid is a property of the shape rather than of the material. If the density isn't uniform, then that center of mass becomes a property of the material as well as the shape. Okay. So if you want, I went through the theorem of Pappus in about 5 minutes last night, just to go through the exercise of showing that this was actually the case. Not really difficult. So I thought it was kind of nice that we have the ability to do something like this. But it's also interesting to think that Pappus came up with this theorem. Pappus, you also hear him referred to as Pappus of Alexandria. He lived in around 300 BC. So he came up with this theorem in around 300 BC before calculus was even well, they were working on ideas that were related to calculus, but integrating was something that was so far off away from the horizon that they couldn't even really imagine it then. So I find that really interesting. And I haven't ever been able to find an argument or a demonstration of how Pappus came up with this result with the mathematics that they knew at the time. All the ones that I've seen involve the stuff that we know. So anyway, there's one interesting extension of centroids, is the theorem of Pappus. The second one has to do with fluid pressure and fluid force. This one doesn't have a fancy name, but our theorem is on a vertically submerged plate, which is what we worked with yesterday. The fluid force F is the weight density of the liquid times H bar times A, where W is the weight density of liquid, and H bar is the depth of the centroid below the surface. And A is the area of the plate. So let me draw a little picture to go with this. Here's our water and our plate here. And it has an area A. And our centroid is somewhere in this region. And we're going to say that's H bar. and this is the centroid. So very similar to the Theorem of Pappus in the sense that it has to do with the distance from the centroid to the surface of the liquid, where the Theorem of Pappus had to do with this distance of the centroid from the axis of rotation. So if we have a nice uniform shape, a circle, a square, something that's really easy to find the centroid, we can find the fluid force on that submerged plate very easily, because we can find the centroid without a lot of work. So we can calculate the area with a lot of work, without a lot of work. So we can find the fluid force on that plate very easily. If our region is more complicated, often it can be as complicated to find the centroid of the region as it is to calculate the fluid force the way we've been doing it.
Is the centroid of a circle just
The center, right. Centroid of the square is going to be the center. So easy shapes, you can figure out where the centroid is pretty easily. So this gives us another little tool, another little application of our centroids relating to some of the other things that we've worked with already. Now, with this idea in mind, you could look back at page 511, number 21 and 22. Number 21 is asking you to demonstrate that this is true. So you just have to, and I think it's for a circle. I think they ask you to demonstrate that it's true for a circle. So number 21 is asking you to prove this theorem, essentially, and then number 22 is an exercise involving this idea. It's not a difficult problem. If you're interested at all, I would suggest you go back and give it a shot. It's not too hard at all. So any questions on our extensions? I just find these little facts really interesting. All right. So today our main topic for the next couple of days is trig substitution. And the reason that we're not really reviewing other techniques of integration, but trig substitution comes up in so many different contexts. And in second semester, when we are working in three dimensions, we'll be doing a lot of stuff with trigonometry. So it's good to look at it again, and maybe see some different applications, or just a reminder of these different applications. So I'm not going to go into a lot of detail on the techniques. We all know how to do it. We all know how to do trig substitution. I just want to give us a reminder and some little pointers on doing trig substitution to hopefully make it easier for you. So, trig substitution is usually used when we have our forms a squared minus u squared, square root of a squared plus u squared, and the square root of u squared minus a squared, where a is some constant and u is some function. We can use it for other forms of integrals, but these are the forms that when you see them, they suggest trig substitution. Why? These kinds of integrals involving these forms, come up a lot. Why do you think that might be? Why would we be interested in integrating quantities that look like this? We're using triangles, and what's our big tool with triangles? The Pythagorean theorem. So this looks like the Pythagorean theorem, and to me, it kind of makes me laugh because a friend of mine has a saying, when all you have is a hammer, everything looks like a nail. So we have this tool, the Pythagorean theorem. Let's make the Pythagorean theorem work whenever we can. So that's kind of the idea. Is we know we can use the Pythagorean theorem. Let's try to make it work. So Pythagorean theorem is kind of like one of our big hammers in math because it always works on right triangles. So whenever I see forms like this, I always think Pythagorean theorem, and that's where we get our triangles. Now, a lot of times in the books, especially, they list when you see this form, you make this substitution. When you see this form, you make this substitution. My suggestion is don't memorize those formulas. Don't memorize. I never remember which substitution to make for which form. I always just draw the triangle, always, no matter what. So that's my first suggestion: is always draw your triangle. I'm a big proponent of not memorizing formulas. If you have a way of getting the result without memorizing a formula, knowing how it works, I feel that that's better than memorizing the formula. I'm not saying don't memorize the formula. I just, if I don't have to memorize it, I prefer not to. If you, what I try to do, this is my personal bias for trig substitution, is I try to get, for my triangle, I try to get u, or whatever my x, whatever my function is, in terms of sine theta, tangent theta, or secant theta. That's my preference, just because that way you usually end up not having to work with the cofunctions. Usually you don't have to work with cosecant and cotangent. So I always try to get my x, my function, in terms of sine, tangent, and secant. You can do it the other way. I have the formulas, the integrals, all of those for sine, tangent, and secant. Those are quicker in my mind than the others. And if you draw a triangle, you don't risk missing a sign. You don't risk switching something around if you make the wrong substitution, or you forget a negative sign. If we are doing definite integrals, remember that to evaluate your integral, if you leave it in terms of theta, you have to change your limits of integration to be in terms of theta, or you have to transform your integral back to the original variable. And we can also use trig substitution for rational powers that involve these forms. So we can use for any rational power. It's easy to forget trig substitution when you have something like u squared minus a squared to the 5 halves. It's easy to forget that could be a trig substitution. And trig substitution is also useful if you don't remember your integral formulas for the inverse trig functions, because you can use trig substitution to find your integral formulas for inverse functions. So again, if you don't memorize those inverse trig function integrals, you can use trig substitution to find them. So just a quick example of that. If we had the integral of 1 over square root of 1 minus x squared dx. If you forgot that this was inverse sine of x plus c, if you forgot that, you can draw your triangle. So I'm going to draw my triangle here, put theta here, And I'm going to set my triangle up this way. So sine theta equals x. My dx equals cosine theta d theta. And the square root of 1 minus x squared is cosine theta for my triangle. So we have, so this integral is the integral of cosine theta over cosine theta d theta, which is just the integral of d theta, which is theta plus c, and theta is the inverse sine of x. So if you don't remember that this is the inverse sine, you can always use trig functions or trig substitution to find your inverse, find your integral in terms of your inverse function. So again, it helps you avoid memorizing formulas. Rational powers. I'm not going to go all the way through some examples. I just wanted to illustrate a couple of things. So for rational powers, what I meant if we had, something like the integral of 1 over x squared plus 3 to the 3 halves dx. I'm going to rewrite that as the integral of 1 over square root of x squared plus 3 to the 3rd dx. And now we have this x squared plus square root of x squared plus 3, which suggests our trig substitution. And if I drew my triangle quickly, I'm just going to draw the triangle. I'm not going to go through the entire integral. For this one, I would draw the triangle. This is square root of x squared plus 3 on the hypotenuse. I would put x here and square root of 3 here. So that would be my triangle for this integral. And this one turns out to be not too bad. So that would be an example of rational power. You can use trig sub for rational powers of your basic forms. And it's easy, when it's written like this, it's easy to forget, oh, what do I do with an integral of this form? If you rewrite it in terms of the radical, then it's a little easier to see. Right, so whatever our substitution is that we make, you have to remember that this third power is out here. So whatever we get, we're going to raise, whatever the substitution for this is, we're going to raise it to the third power. And then the other place where you can apply trig substitution that might not be obvious at first is when we have to complete the square. An example of that would be the integral of dx over square root of x squared plus 4x plus 13. So at first glance, this does not look like it would be trig substitution because we have this trinomial. So what I'm going to do is complete the square in the denominator. So I'm going to say that x squared plus 4x plus 13 equals x squared plus 4x plus 4. So I'm completing the square here, plus 13 minus 4. So I'm adding 4 here, subtracting 4 there. So this gives me x plus 2 squared plus 9. So now I have the integral of dx over the square root of x plus 2 squared plus 9. And this is definitely something that we can use trig substitution on. So if I draw my triangle for this integral, put theta here, this is the square root of x plus 2 squared plus 9. And I did my sides, and this is a squared here. X plus 2 on this side, and 3 on that side. And then I end up with x equals 3 tangent theta minus 2 is my substitution. And this turns out to be not a terrible integral. But at first glance, we wouldn't necessarily guess that this was a trig substitution integral. So completing the square is another place where you can apply trig substitution. Questions? Yes.
With the 3 at the top, the middle one you always with a square plus b squared, the square root implies the hypotenuse when you set a triangle.
Right.
Does it matter for the other two? Like this b squared, does the function have to be in a certain place for the other two, or can you put them on either leg?
You can put them on either leg. Sometimes I'll set it up and I'll say, oh, I got that x equals like cosecant theta. I don't like that. Then I'll switch them around and see if that looks nicer. So you can put them either way.
You can, like for the subtracting, you can square out either the hypotenuse or the
Right. And I pick based on which one I think is going to work the best. They work out the same, just which one's going to be easy. That's how I do it. Let's see. Do I want to say anything else? In your book, let me find the page. They give you they call them special integration formulas. So let me find the page. Take a look at those, and I would suggest that you go through the work to verify those special integration formulas, doing the trig substitution. That's on page 547. They give you 3 special integration formulas. Each of the 3 of those, you can verify by trig substitution. They're not particularly difficult integrals. They do take a little bit of work, but you can do it. Those 3 special integration formulas, we'll see those fairly regularly over the course of the year. So just remember that those special integration formulas exist. When you see an integral that you're not sure that looks like a trig substitution and you're not sure what to do with it, you might think about those special integration formulas. All right, questions? So what we're going to do for today, and then on Monday we're going to do a little bit more with trig substitution. Monday, the assignment for today is just doing trig sub integrals. Practice doing trig sub integrals. The assignment on Monday is applications that involve trig substitution. So fluid pressure, centroids, work problems that involve trig substitution. So applications where you end up with trig substitution. In class on Monday, when you come in, I'm going to have some true-false questions written on the board, and we're going to work in groups and make our argument as to whether that statement is true or false, all having to do with trig substitution. All right. Homework. Couple of hints. Number 41, you have to use integration by parts and trig sub. And for number 51, you end up, in the problem, you end up having to integrate secant cube theta d theta. That is integration by parts. So those are your hints on those problems. And a reminder, the integral of secant theta d theta. Do we remember what that evaluates to? What is it? Very nice. Natural log secant theta plus tangent theta. You might see that integral somewhere in there also.
I don't see a plus C. There we go.
Thank you. All right.